we last left off? What was the last thing that we did?
We did the friction. Well, we like analyzed like if the static is negative.
Okay, that was for box on ramp.
Where we left off.
Yeah. Alright, done facades.
We were doing the box on ramp, but just the box. We did the facades. I think we finished all of them, didn't we?
I was thinking that we did
We
too.
did, and then we got into conversation about acceleration
Good.
in terms of negative and positive stuff. Yeah. Yeah, we finished that.
Alright, let's go through another example before we get into the twist on the same old tale. I do a video of this as well.
Oh, do you need the other information? That should be it. All right, assuming that the rope is long enough, the 2 kilogram mass is not gonna hit the pulley. So the question is, how far up the ramp will the 3 kilogram mass go? And will it slide back down? We're gonna take it step by step. Let's put this, there is ground down here, it's on a bottomless chasm. And let's put this on earth 2. So G is, yep. Oh, I do need to give one other piece of information here. This is the angle.
Is that 130?
Yes, 130 degrees. Now, this is combining some of the stuff we did in the first 2 chapters and in the current force information. So let's start out with doing the facades method, force diagram. Yes, Margaret?
Can you say what the question was for this problem?
The question is, how far up the ramp will the 3 kilogram mass go?
How far up?
Yes. So it has an initial velocity, and it's
Oh, yeah.
going to be dragged backwards, so it will slow down. And the other question is, will the 3 kilogram mass slide back down after it stops
Okay. How far up?
the ramp?
And then will it slide back down?
Yes. Now, so far, we've dealt with problems with we set up our coordinate system so that one of them is in the direction of acceleration and the other is perpendicular to that. We can still do that here. It's not necessarily the simplest mentally to do. Mathematically, it's the same, but conceptually, not necessarily the simplest, but we'll get there. Facades. Let's drop back for just a second. In order to know how far up the ramp it's gonna go, we need to know the acceleration. I know the initial speed, I know the initial direction, so I can figure out the initial velocity. I know what the final velocity is because it's gonna go up until it stops. And I need to know acceleration. And so we'll go through the whole facades method in order to find the acceleration, and then that will help us solve what we need to know here. On a problem like this, ideally on a test, I would give it to you in parts. Now, if ever I give you something in parts, then if you don't solve them in the order, I put them down in the order in which I solve them. If you solve it in a different order, which and sometimes it's convenient to do that, if you solve, just draw some arrows so I know what your thinking was. Now, I've got a lot of objects here. I've got my 3 kilogram object and a marker that just hates life. Got a 3 kilogram object here. Really, I only care about those 2 objects right there. I don't care about the rope per se because it has no mass, so plugging in F equals ma would be, well, 0 equals 0. And the Earth is not moving, we assume. Not yet, at least. But for completeness, let's just go ahead and do the whole thing. All right, force diagram.
Wait, so when you say the rope is ideal, it's frictionless, right?
Yes.
Okay. But would there be friction on the pulley?
No.
Okay.
That's chapter 9.
This would be normal force, because the 3 kg box is actually touching the
So which way is the normal force acting on the box?
southeast ramp and northwest on the box.
Okay. Up and to the left on the box, down and to the right on the ramp. Let's put a little Y, put a little 3 there. I tend to put since I actually have a mass here, I'll use a subscript related to the mass. All right?
There's tension between the 3 kilogram and the rope, so there's gonna be an arrow pointing from the 3 kilogram to the rope, and then there's gonna be one pointing from the rope to the 3 kilogram.
All right, so the one pointing towards the rope, I'm drawing on what object?
The one from the rope, so it's gonna be pointing to the 3 kilogram, right?
No, good. Like that? Is that what you mean?
It would be toward
So the arrow that I'm drawing on the box is pointing which way?
toward the road.
Okay. That's the T, and then. Was that what you meant?
Yeah, I just explained it wrong.
Tension on the tooth daisy
Which way is this arrow drawn?
toward the road. And the road toward.
There's friction between the 3 kilogram and the ground because it's moving by 10 meters per second. So the arrow from the box would be pointing down.
You said from the box. You mean on the box? Because in my mind, on and from are opposites of each other in this case.
It's going a lot better in my head than how I explained it.
You want to come up and draw the arrow that you're talking about? You don't have to, but.
You got it, Rob.
Sure.
It's like it's going.
It's like, it's going.
Okay. So they are on the boxes down the ramp. They are on the ramp is up the ramp.
I guess.
Okay.
I feel like it's the opposite.
Wait, the box is going up though,
Yeah, box is going up the ramp.
Oh,
That's
so,
the problem with setup. The box is initially going up the ramp, so friction is acting
yeah, I think he's right.
yeah.
down. All right,
Weight,
okay.
And then, yeah, there's
weight
weight.
it would be down on the box of 2 kg and up on the ground. And then basically the same thing with the 3 kg.
And where, the ground is a big piece right here. So where you draw your up arrows on the ground, it's up to you. I mean, I drew it here because it's sort of in line with that, but other times I might have drawn W3, the weight 3 going up here, because in the problem over here, that's more in line with it.
So the arrows don't have to like,
Do not necessarily have to point towards each other.
okay.
And drawing them in this orientation is, I find helpful, but in theory, I could have drawn my 3 kilogram mass over here, my 2 kilogram mass here, and they don't have to be drawn for the force diagram in the same orientation. It's just helpful.
Is there normal force from the 2 kilogram in the ground? But it's not touching though, right?
It is not touching,
Okay, so,
so yeah, no normal force there.
and it's not touching the side of the ground, right?
It is not.
Okay, so that's it.
Well, let's go for our checklist there. All right, so I have 2 small objects there, and they both have a weight, and I've got the counter over there, or the other part. Normal force, I've got 3 kilogram mass and ramp. Okay. We're missing a pair of normal forces.
From the rope and the pulley.
There's a reason the rope is built like that. It doesn't naturally want to stay like that. So it is being pushed somewhere in that direction. It's called Y sub R. Y sub R. So normal force done. What about other?
No, wait. The initial velocity, is that the other?
Is that a force?
Yes. No, it's it. It's the velocity.
So what did you decide? Since Robin, apparently you're deciding for the entire group.
I'm saying yes. Because
So what force is it?
it's going to be other, but I don't know how to label it. Is it just going to be the same arrow like that, and then just write down velocity plus 10 meters per
But
second?
we're doing a force diagram though. Velocity doesn't show up in a force diagram.
So it's not part of it. So it's not part of it.
Now, how it got to going that fast in that direction, I don't know. The problem tunes in, we tune in after it's already moving. Maybe it came into existence already moving 10 meters per second up the ramp. So what happened in the past, I don't care about. That it's irrelevant. It's irrelevant about why it's going that fast up the ramp. The question is what's happening at this moment. And there is no force. I think those would be the only forces. There's no other, that's what we're heading towards. Tension, we got tensions at each end. And friction, I got only 1 pair, yeah, there we go.
So how would you label in a force diagram when there's an other force?
It depends. If I put in hand of God there to push it one way or the other, then I usually just label it whatever the value is, because, or F applied,
Okay,
whatever seems appropriate for the problem.
alright.
Now what?
Direction, acceleration.
Yes, what about it?
Is going to be, the direction of acceleration should be the same direction as the initial velocity.
Why?
Because I said so.
I like it.
I missed, you trailed off there, and my hearing's not good enough.
I said, because I said so. for-
Yeah, that's not the right place.
Really? But, oh wait, is it, did you say it was slowing down?
It shouldn't it be the opposite of the initial,
Why?
because so.
No.
Wait, in the question, did you say it was slowing down, it was going up?
If I had a situation like this, where I had something moving up a ramp, attached to some dangling mass right here,
It should be slowing down. So,
Yeah,
direction
is-
should be anti-parallel.
we can't just let anything goes here, that's for quantum physicists and mathematicians.
Okay.
This is a classical physics.
Okay,
Yeah,
wait.
I would assume it's slowing down.
It's
Okay.
going up.
So it's so it's supposed to be anti-parallel from the initial velocity.
It will be in this case.
Okay.
Now, another way of looking at it is if the acceleration is up the ramp, if it were up the ramp, there would have to be some force acting up the ramp on the box, and there is no force acting in that direction on this box. There's no way it could accelerate up, or we've left something off.
Okay.
Now, some students want to bring in that fact that it's going up the ramp, and so there must be a force there. No, that's the wrong way of thinking about it. All this is I have a velocity, and that is not part of a force diagram.
Wouldn't that technically be an other though as well, if we don't know what's acting up on the 3 kilogram box? That would be considered an other?
If, let's say you closed your eyes, you don't need to close it, but if you close your eyes and I roll the ball past you, and you open your eyes and you see the ball go past, does that mean that I still have power over it? That I can somehow move objects from a distance?
No.
Same thing here. All we're doing is we tune in, it's already
Then how's it
moving.
going up?
Pardon?
How's it going up?
I don't know. It just, that's the problem.
Okay.
How it got to that point, how it got to this situation is before the problem, before we come into it. We cannot predict the past. We have to look at this and we can make predictions about the future. The future is more certain than the past. I don't know how it got this way,
Okay.
but all I know is that it got this way.
So then we don't know, so that's an other.
And the other is we don't know what's causing the force at that moment. There's no other force. If you're making the assumption that it started at rest at some point and something pushed it to get it going, is that correct?
Sure.
Or not?
You said so, so yeah.
No, I didn't.
No.
I'm trying to figure out what you're thinking
Keep
is.
going, keep going.
I mean, a number of students, not necessarily you, a number of students will look at that and figure it started at rest at some point, therefore some force had to get it going.
Right.
I'm saying we don't know that.
So we just know it's there.
So if
So-
we did know it, then other would be identified.
If we were looking at that part of the problem.
Okay.
If I throw a ball into the air, as soon as it leaves my hand, yes, my hand, the normal force was what got it going. But once it leaves my hand, that normal force doesn't exist anymore.
Okay.
And so we're coming into it after whatever created this. Maybe it came, some things come into existence already moving. Now, from my own personal experience, I'm not used to things just materializing out of thin air already moving. But we cannot, it is a non-zero possibility, probability. It is possible that all those particles came into existence with it already moving. In the same way, we have no idea if any of us woke up this morning. It's possible that we were all created at this very moment, coming into existence, thinking the thoughts we're thinking.
Just 'cause I just
This is
imagine that.
actually the truth.
So here's how we can imagine the problem. I went hiking and then I see a ledge and then I just see that there.
Not just,
That's it.
Yes,
just in here.
we are not analyzing the past, we're analyzing the present,
Okay.
making predictions about the future. All right. I hope we're okay with not, there is no other.
So acceleration is going anti-parallel.
Yeah, so acceleration is down the ramp. So just not part of the force diagram, just fine. So that's accelerating that way. And what about the 2 kilogram mass?
Straight down.
Yep.
Oh, there's two.
It's a tight string. I mean, it's not like the 2 kilogram mass is going up, is accelerating upwards, the other one's accelerating downwards. That would put a lot of slack on the rope of tension with this one. All right, so we have a direction of acceleration now. So now the coordinate system. I do recommend that whatever coordinate system we set up, that we treat A's the same. That if we want that to be the positive direction, then that's the positive direction for this 2 kilogram mass. If we want that to be the positive direction for the 3 kilogram mass, then that's the positive direction for the 2 kilogram mass. We don't have to, but it saves us having to think about whether we need an extra minus sign there or not. So, the question is, do you want positive acceleration or negative acceleration?
Positive.
You want positive acceleration?
Yes.
And it's been set, so it's good. So we'll set up our coordinate system so that we have, I'm gonna call this I3 hat, and away from the ramp or towards the ramp?